Good morning, learners and viewers. Welcome to the session of Master of Business Administration. Today we will be talking about Operational Research MMPO 001. In today's session, we will be talking and discussing about game theory and its application. To start with, game theory seeks to analyze competing situations which arises out of conflicts of interest. Abraham Maslow's hierarchical model of human needs lays emphasis on fulfilling the basic needs such as food, water, clothes, shelter, air, safety, and security. There is a conflict of interest between animals and plants in the consumption of natural resources. The conflict of interest of human beings are not confined to the basic needs alone. Again, considering Abraham's Maslow's law model of human needs, one can realize that conflicts also arise due to higher levels of human needs such as love, affection, affiliation, recognition, status, dominance, power, esteem, ego, self respect, etc. Sometimes one witnesses clashes of idea of intellectuals also. Every intelligent and rational participant in a conflict wants to be a winner, but not all participants can be the winner at a time. Game theory is another tool to examine situations of conflict so as to identify the courses of action to be followed and to take appropriate decisions in the long run. Thus, this theory assumes importance from managerial perspectives. The pioneering work on the theory of games was done by von Neumann and Augustin through their publications entitled The Theory of Games and Economic Behaviors. And subsequently, the subject was developed by several experts. What is the definition of game theory? The definition given by William G. Nelson runs as follows. Game theory, more properly the theory of games of strategy, is a mathematical method of analyzing a conflict. The alternative is not between this decision or that decision, but between this strategy or that strategy to be used against the conflicting interest. According to von Neumann and Modestin, the game is simply the totality of the rules which describe it. Every particular instance at which the game is played in a particular way from beginning to end is a play. The game consists of a sequence of moves and the play of a sequence of choices. What are the concepts in the theory of game? Several of the key concepts used in the games are discussed below. What is game? A competitive situation is called a game if it has the following properties. There are finite number of participants called players. Each player has finite number of strategies available to him, and every game result in an outcome. What is players? The competitors or decision makers in a game are called the players of the game. What is strategies? The alternative courses of action available to a player are referred to as his strategies. Generally, two types of strategies are employed by players in a game. First one is pure strategy. It is the decision rule which is always used by the player to select any one of a particular course of action. The objective of the player is to maximize gains or minimize losses. Second one is mixed strategy. When the player uses a combination of strategies and each player always keep guessing as to which course of action is to be selected by the other on a particular occasion, then this is known as mixed strategy. Thus, the mixed strategy is a selection among pure strategies with fixed probabilities. Payoff. The outcome of playing a game is called the payoff of the concerned player. Payoff matters. The tabular display of the payoffs to a particular players under various alternatives is called the payoff matrix of the game. We will be using this when we will be solving the numerical part of it. Zero sum game, a game in which the total payoff of all the players at the end of the game is zero, which is referred as zero sum game. Non zero sum game, games with less than complete conflict of interest, are called non zero sum games. The problems faced by a large number of business organizations come under this category. In such games, the gain of one player in terms of his success needs to be completely at the expense of the other player. Now comes saddle point. A saddle point of a game is that place in the payoff matrix where the maximum of the row minimum is equal to minimum of the column maxima. The payoff at the saddle point is called the value of the game, and the corresponding strategies are called the pure strategies. Fair game. A fair game is said to be fair if v underscore is equal to 0 is equal to v bar. Dominance. One of the strategies of either player may be inferior to at least one of the remaining ones. The superior strategies are said to dominate the inferior ones. Types of games. There are several classifications of a game. The classification may be based on various factors such as the number of participants, gain or loss to each participant, the number of strategies available to each participant, etc. Some of the important games are two-person games and n-person games. In two-person games, there are exactly two players, and each competitor will have a finite number of strategies. If the number of players in a game exceeds two, then we refer to as a game with n-person games. Zero sum game and non zero sum game. If the sum of the payments to all the players in a game is zero for every possible outcome of the game, then we refer to the game as zero sum game. And if the number of payoffs from any one of the game is either positive or negative but not zero, then the game is called the non-zero sum game. What are the basic assumptions of the game? The rules of the game are as follows. Each player has available to him a finite number of possible courses of action. The list may not be same for each player. Players act rationally and intelligently. The decision of the both the players are made individually prior to the play with no communication between them. If one player attempts to maximize gains and the other attempts to minimize its losses, the players simultaneously select their respective course of action, and the payoff is fixed and determined in advance. What is the procedure of determining saddle point? Select the minimum element in each row and enclose it with a rectangle. Second, select the maximum element in each column and enclose it with a circle. Find the element which is enclosed by the rectangle as well as by the circle, and such element is the value of the game, and that position is a saddle point. Now comes what are the managerial applications of the game theory. The technique of game theory can be effectively applied to various managerial problems, such as to analyze or the analysis of the market strategies of a business organization in long run, evaluation of the responses of the customers or the consumers to a new product, and resolving the conflict between two groups in a business organization. Now, we take up a problem. We have the statement will be as solve the game with the following payoff matrix. We have strategies, and in the rectangle we can see that there are different values. These are the payoffs, and they are being placed in a column and row combination. That is known as payoff matrix. On the left side, we have player A and its strategies, and on the top, we have player B and his strategies. As for the steps of the game theory, we have to find out the row minimum. First of all, so we get row minimum at -3, row 2 minimum is -1, row 3 minimum is 2, and row 4 minimum is 12. This can be written as we have to find maximum of this. The maximum of this row element will be from the -3, -1, 2, and 12, and the maximum value is 12. Now we consider the column. In column 1, we have 15 as the maximum value. Column 2, we have 14. Column 3, we have 18. Column 4, we have 12. And column 5, we have 20. From that, we have to see what is the maximum of row minimum should be equal to minimum of the column maximum, so that the game has a certain point. And this common value is 12. That means the value of the game is 12. Now, what we are going to interpret from these numbers. In a long run, the following best strategies will be identified by the two players. The best strategy for player A is strategy 4, and the best strategy for player B is strategy Roman 4. That means a game is favorable to player A. Now, games with no settle point. If we take up an example of 2 by 2 zero sum game, where each of the first player A and second player B has exactly two strategies, we have a 2 by 2 game. When maximum row minima and minimum column maxima are not equal, and that game has no settle point. Now, what is the method of a solution to a 2 by 2 zero sum game without settle point? So we have a 2 by 2 matrix which has no settle point. Suppose the payoff matrix is given by A, B, C, D, and the representation remains the same. Player A strategy on the left side and player B strategy on the top side. We have, since we have no settle point, in that condition, this statement holds correct that maxima of minima AB, minima of CD is not equal to minima of maxima of AC and maxima of BD. The matrix, payoff matrix is on your left side. In this case, the game is called a mixed game. No strategy of player A can be called the best strategy for him. Therefore, A has to use both of his strategies. Similarly, no strategy for player B can be called the best strategy for him also, as he has to use both the strategies of. Let P be the probability that player A will use his first strategy. Then the probability that player A will use his second strategy will be 1 minus B. Now, if a player B follows his first strategy, expected value of payoff to the player A will be expected value of the payoff of player A arising from his first strategy plus expected value of the payoff of player A arising from his second strategy. So mathematically, in a equation form, it can be written as, or in a representation form, it can be written as A into P plus C into 1 minus P. Similarly, for player B, his expected value for payoff of player A will be equal to Bp plus D into 1 minus P. If the expected values in equation 1 and 2 are different, but player B will prefer the minimum of the two expected values, then he has to give a player A. Thus, we will have a pure strategy. This contradicts our assumption that the game is a mixed one. Therefore, the expected values of the payoffs to player A and in equation 1 and 2 should be equal. So we have the following conditions. P is equal to D minus C upon sum of A plus D minus sum of P plus C. Similarly, Q will be A minus B upon sum of A plus D minus sum of D plus C. That means we can say that the expected payoff to player A is AD minus BC upon A sum of A plus D minus sum of B plus C. And the value of the game will be similar. AD minus BC upon sum of A plus D minus sum of B plus C. In short, we can use this formula. If 2 by 2 game is given to us and it is without certain. So directly we can apply this formula and the payoff matrix of player A is given to us. Suppose the values are A11, A12, A21 and A22. So we can straight away find out P1 equal to A22 minus A21 divided by sum of A11 plus A22 minus sum of A12 plus A22. And Q1 will be A22 minus A12 upon sum of A plus 11, A11 plus A22 minus sum of A12 plus A2. P2 will be 1 minus P1 and Q2 will be 1 minus Q1. Value of the game A11 product of A11 and A22 minus A21 A12 divided by sum of A11 plus A22 minus sum of A12 and A21. Now we take up a problem. In a game of matching coins with two players, suppose A 1 unit of value, then there are two heads. Wins nothing when there are two tails and losses 1 by 2 units of value when there is one head and one tail. Determine the payoff matrix, the best strategies for each player, and the value of the game. So here we can see that there are two players and two outcomes are there. So initially to start with, on the left side, we will write player A and its strategies will be A1 and A2. And similarly on the horizontal part, we will write player B. Its strategies will be noted by B1 and B2. Now we will find out from the statement, we will find out the payoff matrix. So initially we will start with 1 minus 1 by 2 and minus 1 by 2 and 0. This payoff matrix does not have a saddle point. That means we have to use algebraic method to solve it. We know, we remember the formula. Suppose We have to initially find out the value of P1, P2, Q1 and Q2 and the value of the gain. So we have standard formulas. We can use that. So initially for P1 we will be using A22 minus A21 upon the sum of A11 plus A22 minus sum of A12 plus A2. Going back to the matrix, original payoff matrix, we will find out the values of A22, that is 0, A21 is minus 1 by 2, and A11 is 1, A22 is 0, A12 is minus 1 by 2, and A21 is minus 1 by 2. After calculating this, we will get 1 by 4. Since P1 is 1 by 4, so P2 will be 1 minus P1. That will be 1 minus 1 by 4, which is 3 by 4. Now, for player B, Q1 is equal to Q22 minus Q12 whole divided by A11 plus A22 minus sum of A12 plus A2. So we will be straight away putting up the values from the payoff matrix. We will get again 1 by 4. And Q2 will be 1 minus Q1, which will be 3 by 4. Now to calculate the expected value of the gain, we again have a standard formula A11 multiplied by A22 minus the product of A21 and A12 divided by the sum of A11 plus A22 minus sum of A12 plus A2. After putting up the values, we are going to get minus 1 by 8. Now we take a problem here which is not a 2 by 2 matrix form, it is 2 by 3. We have to find the optimum strategies for player A and B. We have to determine the value of gain and we have to also show that is this a game fair one or it is strictly determinable. We will be finding out, as discussed earlier, we will be finding out initially the saddle point, if it exists. So select the row minimum and enclose it with a rectangle. Then select the column maximum and enclose it with a circle. Initially in row 1, we get minus 2 and in column section we get again minus 2. That means we have a saddle point that is minus 2, which is in row A1 and column B3. So that means saddle point will be A1, B3. That is, it is the both minimum of the column maxima and maximum of the row minimum. The value is referred to as saddle point. Value of the game is minus 2. And the payoff amount is the saddle point. Position is also called the value of the game. Optimum strategy for A is A1 and for B it is B3. The game is strictly determinable since value of game is not 0 and the game is not fair. Now we take a problem which is related to 5 columns and 4 rows. The method is not going to change. We have to find column maximum. We have to find first column row minimum. Row minimum for the A1 is minus 2, A2 is 1, A3 is minus 4, and A4 it is minus 6. And as column maxima is concerned, for B1 it is 5, B2 it is 3, B3 it is 1, B4 it is 5, and B5 it is minus 6. The maxima of minima, that is 1, minima of our maximum row, it is 1. That means there is a saddle point because maximum minima of row and maximum minima of column are the same values. That means the value of the game is 1. The position of the saddle point is the optimum strategy and it is given by A2, B3. Dominance. In game theory, dominance occurs when one strategy is better than the other strategy for one player, no matter how that player opponents may play. Many simple games can be solved using dominance. The opposite intransitivity occurs in the games when one strategy may be better or worse than other strategy for one player, depending on how the player's opponent may play. The concept of dominance is very useful for reducing the size of the game. Applying this concept, we can convert a bigger game into a smaller one. Hence, we must examine the possibility of reducing the game size using the principle of dominance. What are the rules of for dominance? If all the elements in a column are greater than or equal to the corresponding elements in another column, then that column is dominant. Similarly, if all the elements in the row are less than or equal to the corresponding elements in the other row, then that row is dominated. Dominated row or column may be deleted, which reduces the size of the game. Always look for dominance when solving a game. Now we take up a problem. We have to determine the optimum strategies and the value of the game from the following payoff concerning to two persons 4 by 2 game. We will first of all find out the setting point. There is no setting point in this game. This game also cannot be solved by dominance because there is no row which is always preferred by x. Irrespective of what y do, player X can actually think of his 4 by 2 game as being 6 sub games, each of 2 by 2. These 6 sub games can be enlisted as initially we will be taking -6, -2, -3, -4. The strategies will be noted as we have to calculate the value of the game. It will be -6 into 1 by 5 plus 4 by 5 into -3. That comes out to be -3.60. We will move to another strategy to find out the payoff method. Its value will be 11 by 15 into -6 plus 4 by 15 into 2, which comes out to be 50 minus 58 by 15, which is almost equal to -3.87. And similarly, we will be finding out for the other subgames. There is a saddle point here in third subgame. The value of the subgame is -6. And in subgame number 4, again with there is a saddle point and the value of the subgame is -4. In subgame number 5, there is no saddle point, so that means we have to calculate its value. Its value will be 6 by 7 into -3 plus 1 by 7 into -7, which comes out to be -3.57. And for subgame number 6, strategies are as follows, and we have to find out the value. That will be 6 by 17 into 2 plus 11 by 17 into -7, which comes out to be -3.82. On looking at the values of these subgames, we find that the value being negative, y will win and x will lose in all the cases. Player X, who is making the choice, will naturally prefer the subgame with smallest negative value, and that is for subgame number 4 for this problem. Thus, X will play a two-row mixed strategy between second and fourth row of the original game, and he will expect to lose an average of 3.57 points per play of the game, which will be his minimum possible loss. Being an intelligent opponent, player Y will also adopt a strategy consisting of the same number of columns. In brief, we can say that subgame number 5 strategies will be adopted by players X and Y with a game value equal to minus 3.57. Now we move to simulation. We will be talking about Monte Carlo simulation. First of all, what simulation is? Simulation is the most important technique used in analyzing a number of complex systems where the methods discussed in previous chapters are not adequate. There are many real world problems which cannot be represented by a mathematical model due to stochastic nature of the problem, the complexity in the problem formulation, and many values of the variables are not known in advance, and there is no easy way to find these values. Simulation is a representation of reality through the use of model or other device, which will react in the same manner as reality under a given set of conditions. Classification of simulation model. Simulation models are classified as simulation of deterministic models. In the case of these models, the input and output variables are not permitted to be random variables, and models are described by exact functional relationship. Second one is simulation of probabilistic models. In such cases, method of random sample is used. The technique used for solving these models are termed as Monte Carlo technique. Simulation of static models. These models do not take variables time into consideration. And the fourth one is simulation of dynamic models. These models deals with time varying interaction. What are the advantages of simulation? Simulation is a widely accepted technique of operations research due to the following reasons. It is a straightforward and flexible. It can be used to analyze large and complex real world situations that cannot be solved by conventional quantitative analysis models. It is only method sometimes available. It studies the interactive effect of individual components of variables in order to determine which one are important. Simulation model, once constructed, may be used over and again to analyze all kinds of different situations. What are the limitations? Since simulation model mostly deals with uncertainties, the result of simulation are only reliable approximations involving statistical errors. Optimum results cannot be produced by simulation. In many situations, it is not possible to identify all the variables which affect the behaviors of the system. In very large and complex problems, it is difficult or sometimes very difficult to make the computer program and view of the large number of variables and the involved interrelationship among them. For problems requiring the use of computer, simulation may be comparatively costlier and time consuming in many cases. Each situation solution model is unique, and its solutions and inferences are not usually transferable to other problems which can be solved by other techniques. Monte Carlo simulation is a method of simulation technique in which statistical distribution functions are created using a series of random numbers. Working on the digital computer for a few minutes, we can create data for months or years. This method is generally used to solve problems which cannot be adequately represented by mathematical models or where solution of the model is not possible by analytical method. Monte Carlo simulation yields a solution which should be very close to the optimum but not necessarily the exact solution. Monte Carlo, what is the procedure? Step 1, clearly define the problem. That means identify the objectives of the problem. Identify the main factors which gives the greatest effect on the objectives of the problem. Second one, construct an appropriate model. Specify the variables and parameters of the model. Formulate the appropriate decision rules, that is, the state the conditions under which the experiment is to be performed. Third one is identify the type of distributions that will be used. Models use either theoretical distributions or empirical distributions to state the pattern of the occurrence associated with the variables and specify the manner in which the time will change. Now we take up a problem to understand what this Monte Carlo simulation is. With the help of a single server queuing model having inter-arrival and service time constantly 1.4 minutes and 3 minutes respectively. Explain discrete simulation technique, taking 10 minutes as the simulation period. Find from this average waiting time and percentage of idle time of the facility of a customer, assuming that initially the system is empty and the first customer arrives at time t. Now, what is the data and how that has to be transformed? Data, the system is initially empty. Service starts as the first customer arrives. That is, when the first customer arrives, the time is equal to 0. The departure time of the first customer is 0 plus 3. That is the arrival time plus the service time. The second customer arrives at 1.4 minutes and the third arrives at 2.8 minutes. Until the first customer leaves the system, second and third will have to wait in the service. We can calculate waiting time for second customer by taking the difference of time of departure of the first customer and the time of arrival of the second customer. That is 3 minus 1.4, which comes out to be 1.6 minutes. Now we will be developing that information into a tabular form. A tabular form, we have to calculate the waiting time. Waiting time for all the customers will be calculated. That means we have to calculate the average waiting time per customer for those who must wait. Sum of waiting time for all customers divided by the number of waiting times taken. We have 7 over here. Initially it is 1.4, then it comes down to 2.8, then 4.2, 5.6, 7.0, 8.4, 9.8, and it's divided by 7, which comes out to be 18.8 divided by 7. And your answer is 2.7 minutes. Percentage of idle time of the server is equal to sum of the idle time of the server divided by time, which comes out to be 0%. Now, we will take another problem to understand in different condition. The management of ABC is considering the question of marketing a new product. The fixed cost required in the project is rupees 4,000. Three factors are uncertain, that is the selling price, the variable cost, and the annual sales volume. The product has a life of only 1 year. The management has the following data with three factors, and the respective probability is given. If the selling price is rupees 3, its probability is 0.2. If variable cost is 1, its probability is 0.3. If the sales volume, that is in units, the probability is 0.3. Now, how to solve this problem? Considering the following sequence of 30 random numbers, these numbers are given to us. Using the sequence, the third random number for the first try, etc. This is what we will be following. Simulate the average profit for the above project on the basis of 10 tries. So how this information will be converted into a problem solving technique. The cumulative probability distribution and random interval for selling price, variable cost, and sales volume is developed. Probability was given to us and the selling price was given to us in the initial problem. So we have to calculate the cumulative probability. Cumulative probability is what? 0.2. In the initial row, it will be 0.2. And for the second, we will be adding 0.2 plus 0.5, which comes out to be 0.7. And for the third one, we will be adding 0.7 plus 0.3, which comes out to be 1. Now we have to find out the random numbers of the interval. This we will be finding out by the numbers what we are given. No doubt we have to start with 0 and we will be moving to 19. And in the second, we will be moving from 20 to 69. And for the third, we will be moving from 70 to 99 because we have two-digit random numbers. Initially, the same thing will be followed for variable cost and for the sales volume. After this, another table is formed. This table at the bottom consists of number of trials, random number, selling price, random number, variable, random number, and sales volume. These numbers are taken from the numbers what we are given to us in the basic problem. Then we have to find out the average profit per trial. For that, what we will be doing, how profit is calculated. Profit will be calculated from the above table. Profit is selling price minus variable cost into sales volume minus fixed cost. So we will be finding out the selling price for the trial one, the variable cost, and sales volume minus the fixed cost. Fixed cost is the fixed amount. It will be for all the 10 observations as 4,000. Variable sales volume is going to change. It is given to us in the original problem. And from the selling price, the variable cost has to be calculated from the above. We get the value as total value is 21,000 and the average profit per trial will be divided by number of the observations, that is 10. That comes out to be rupees 2,100. Now, simulation of maintenance problem. A plant has a large number of similar machines. The machine's breakdown or failure is random and independent. The shift in charge of the plant collected the data about the various machines' breakdown time and repair time required on hourly basis and the record for the last 100 observations. This data is given to us what the shift manager, shift in charge generate. For each hour that one machine is down due to being or waiting to be repaired, the plant loses rupees 70. By what way of lost production? A repairman is paid rupees 20 per hour. In that case, what we have to simulate this maintenance system for 15 breakdowns. And how many repairmen should the plant hire for repair work? So we will be calculating as what we have done in the last problem. We will be converting this data into a random number coding for the hourly breakdowns and the repair times. It is shown in the table. It starts from 0.51, 1.52, 2.5, and 3. And the respective probabilities are 0.05, 0.06, 0.16. We have to calculate the cumulative probability. That is, initially it will be 0.05 plus 0.06. That comes out to be 0.11. We have to add 0.16, which comes out to be 0.27. Until the last, we have to calculate it. And similarly, we have to use random number range. How the next third step is to generate random number coding for repairs. Left one is for the breakdown, the right one is for the repairs. The simulation worksheet is shown in the table. It is assumed that the first day begins at the midnight, 0 hours, and also that the repair one begins work at 0 hours. The first breakdown will occur at 2:30 a.m. and the second occurs after 3 hours. That means at 5:30 a.m. Now this table is generated according to the calculation what has been provided in the problem. We have to calculate number of breakdowns, random number of breakdowns, time between the breakdowns, time of the breakdown, repair work begins at, random number of repair work on the table, repair time required, repair work ends at, and what is the total idle time, and how much is the waiting time. Because we are calculating all this because we have to calculate the amount. The total current maintenance cost is sum of idle time cost plus repairman's wages, which is calculated as repair sum of repair time plus waiting time into hourly rate plus total hours into hourly wages, which comes out of from taking up all the values from the table. We get 4,777. Now we have to move to the another part of the problem. Maintenance cost with additional repairmen. If the plant hires two repairmen, then no machine will wait to be repaired. Thus, the total idle time would be by repairing time of 36 hours. Therefore, the total cost will be 36 into 70 plus 38.30 into 2 into 20, which comes out to be 4,052 rupees, which shows that hiring one more than two repairmen would only increase the total maintenance cost. Hence, the plant should ideally hire one additional repairman. Now we move to queuing theory. A common situation that occurs in everyday life is that of waiting in a line either at bus stop, petrol pump, restaurant, ticket booth, doctor clinic, bank counter, traffic lights, and so on. Queues, that is waiting lines, are also formed in workshops where the machines wait to be repaired, at a tool club where the mechanic wait to receive tools, in a warehouse where items wait to be used, incoming calls wait to mature in the telephone exchange, trucks wait to be unloaded, airplanes wait either to take off or to land, and so on. These are the basic practical problems. A queue is formed at a production operation system where either customers, human beings, or physical entities requiring service waits because number of customers exceeds the number of service facilities, or service facilities do not work efficiently, or they take more time than prescribed to serve a customer. Queuing theory can be applied to a variety of situations where it is not possible to accurately predict the average rate of customers and service rate, which is in time, of the service facilities of facility. In particular, it can be used to determine the level of service, either the service rate or the number of service facilities that balances the following two conflicting costs. The first one is cost of offering the service, and the second one is cost incurring due to the delay in offering service. The first cost is associated with the service facilities and their operations, and the second cost represents the cost of customers waiting for service. An increase in the existing service facilities would reduce the customer's waiting time. Conversely, decreasing the level of service would result in long queues. This means an increase in the level of service increases the cost of service facilities, but decreases the cost of customers waiting for service. Figure which is shown at the bottom illustrates both types of cost as a function of level of service. The combined cost of service and customer waiting cost is U-shaped because of the trade-off relationship. The total cost is minimized at the lowest point of the total cost curve. The service level is one that minimizes the sum of the two costs. Since customers' waiting cost for service is difficult to estimate, it is usually measured in terms of loss of sales or goodwills when the customer is a human being and has no sympathy with the service system. But if the customer is a machine waiting for repair, then cost of waiting is measured in the cost of in terms of cost of lost production. Many real-life situations in which study of queuing theory can provide solutions to waiting line problems are listed in the table. We can refer to the situation is petrol pumps, the customer is automobiles, and the service facilities are pumps and personnel. If we take a case of hospital, that is customers are patients, and the service facilities are doctors, nurses, rooms. And if we talk about uh, cargo, it is truck, customers are truck, and the service facilitators are loaders and unloaders. The structure of a queuing system. The major component or parts of element of any waiting queuing system are shown in the figure. Each of these components are discussed below. We will start with calling population or the input input source. Second one is queuing process. For what process they are into the system and why they are waiting. Third one is queue discipline. And the fourth one is service process. Potential customers who arrive in the queuing system is referred as calling population, which is also known as customer input source. The manner in which the customer arrives at a service facility, individually or in batches, at scheduled or unscheduled time, is called the arrival process. The customer's entry into the queuing system depends upon the queue condition. Customers from a queue are selected for service according to certain rules which are known as discipline, queue discipline. A service facility may be without server or may include one or more servers operating either in a series or in parallel. The rate at which service is rendered is known as service process. If the server is ideal at the time of customer's arrival, then the customer is served immediately. Otherwise, the customer is asked to join a queue or waiting line, which may have single, multiple, or even priority lines. Calling population characteristics. The arrival or input to the system are characterized by size of calling population, behavior of the arrivals, and pattern of the arrival at the system. The calling population needs to be homogeneous and may consist of several subpopulations. That is, if we take an example of patients arriving at the OPD of a hospital are usually of three categories: walk-in patients, patients with appointment, and emergency patients. Each patient class places different demands on service facility, but the waiting expectations of each category differs significantly. Size of calling population. If popular probability of an arrival depends on the number of customers already in the system, the calling population is called limited or finite. The problems of finite population are queuing systems that have limited access for service such as operators responsible only to handle five machines. Secondly, salesmen responsible to handle limited number of customers, etc. Or if the probability of an arrival does not depend on the number of customers already in the system, The calling population is called unlimited or infinite. Problems of infinite population are those open to the general public, such as banks, supermarkets, petrol pump, ticket counters, because in such a queuing system, customers already present do not decrease potential of others in the population to enter the system. Behavior of arrivals. If a customer on arriving at the service station waits in the queue until served and does not switch off between the waiting line, he is called a patient customer. Machine arrived at the maintenance shop are the problems of patient customers. Whereas the customers who wait for a certain time in the queues and leave the service system without getting service due to certain reasons is called an impatient customer. With this, we will be ending this session.